In this video, I'm planning on going over how to solve this nozzle problem. So this is number 5-29 in Thermodynamics, an Engineering Approach, CBK, and this is the 8th edition. This problem is probably in the other editions. It will just be a different number. So I'm going to approach this problem the same way I'm approaching all of them. First of all, I'm just going to write down what I'm going to do. So first I'm going to write down problem, info, drawing, and so the problem info would be like all the knowns, unknowns, etc. So the whole point of this is to just kind of figure out what the problem's even asking for, figure out what information you already know, what information you need to find, and then a drawing usually helps to kind of visualize what's going on. So the second step is I'm going to write down assumptions. So in order to solve any sort of engineering problem, we need to make assumptions in order to make the problem solvable. So that's going to always be a step for solving engineering problems. Is you need to figure out what are you assuming about your system. Like, is it flow? Is it adiabatic? Is it ideal gas? So just think about all the different things that could go into assumptions that will make reasonable sense that can help you solve the problem. The third step is to write down the equations you're going to use. And so this would be like the first law for this class. If you ever need an energy balance, that would be basically the first law. Do you have ideal gases? Like, do you need ideal gas equations? Are they polytropic? Do you need the polytropic equation? So just try and list the various equations you're going to use at this step. The fourth step is to look up data. So this would be, do you need any data from the tables? This is where you'd look it up. The fifth step is to solve your equations. And I kind of mix, so these last three, I basically do them in this order, but I might sometimes mix them up a teeny bit because sometimes I'll write down an equation and I won't find a second equation that I need until I'm working through that equation, so I'll start solving it, and then it's like, oh, I actually need this other equation too, and so then I kind of go back and figure out the second equation. So if you don't get everything on each step, that's fine. This is just the general steps that you want to follow to try and get your problem set up the same way each time. And it's going to make it a lot easier to solve these problems if you have a set way that you always approach solving them. So let's look at this problem. So it says air at 600 kilopascals and 500 Kelvin enters an adiabatic nozzle that has an inlet-to-exit area ratio of 2:1 with a velocity of 120 meters per second and leaves with a velocity of 380 meters per second. Determine the exit temperature and the exit pressure. So basically we have a nozzle and it says that it's adiabatic. So remember that a nozzle increases the velocity of your fluid. And it's adiabatic, so that means there's no heat transfer in or out of the nozzle. Nozzles don't usually have work, they're passive. And it tells us the temperature and pressure at the entrance. It tells us the entrance and exit velocities, and it tells us a ratio between the entrance and exit areas, and then it wants us to find the exit temperature and pressure. So let's go ahead and start with step one. So step one is to write down the problem information, drawing, and write down our knowns and unknowns. So first of all, we have a nozzle. So I'm going to draw a nozzle. And even though it's pretty easy for me to visualize a nozzle, I always draw one just so it's really clear what I'm doing. Like even if I have a problem where my system might be a rigid volume or a rigid container, I still draw a rigid container because it just makes it easier to just glance at the problem and visualize, okay, this is what I have, this is what's going on. Because I think the thing that sometimes makes these problems hard is they can seem kind of abstract. So the more that you can kind of visualize the problem, the easier it's going to be. So we have air in the nozzle, and it tells us that it gives us the pressure and temperature in, or at the entrance. So P1 is 600 kilopascals, T1 is 500 Kelvin, and then it tells us our entrance velocity is 120 meters per second. Our exit velocity is 380 meters per second. And then I'm going to put P here. So we're looking for P2 and T2. So the exit pressure and temperature. It tells us that it's adiabatic, so that just basically means it's well insulated. So Q dot is equal to 0. Work is also equal to 0 because it's a nozzle. And it also tells us that the area, so I'm just going to put this here, so the area in to the area out is 2 to 1. And so basically it's saying that the area of the inlet is twice as big as the area of the outlet. And that kind of makes sense because our nozzle is the area at the entrance is going to be larger than the exit. Okay, so I think that is most of our information. There might be a few more things that we need to look up as we go along, but this is basically our problem information, drawing. We have a pretty clear idea of what we're solving for, the pressure and temperature at the outlet. And so now the next step is to write down some assumptions. So number 2, assumptions. And I'm just going to call this one, I'm just going to call this problem setup. All right, so let's go through some assumptions we can make. First of all, this is a nozzle, and the problem statement hasn't said anything about it being in a startup or shutdown phase. So that basically means that the mass flow in has to be equal to the mass flow out. So basically we're going to assume steady flow. So m dot 1 is equal to m dot 2 is equal to m dot. And this makes sense because if we have air or fluid flowing through this nozzle, we can't really have, unless it's in the startup or shutdown phase, we can't really have the mass changing inside the nozzle with time. Otherwise, it wouldn't be operating correctly. So basically, since it's a nozzle, we can assume steady flow. We have air, and we want to know if it's ideal. So do we have an ideal gas? Well, let's look at our critical temperature and pressure and for air. And just by eyeballing this problem, we should probably already be able to kind of tell that it's probably ideal because we have air, we have a pretty high temperature, pretty low pressure. But let's just write down the critical temperature and pressure for air so that we can verify whether or not this gas or this air can be treated as ideal gas. So the critical temperature of air is 132.5 Kelvin. And this is just something that you will look up on a table. The critical pressure of air is 3.77 megapascals. So we just verified our temperature is 500 Kelvin at the inlet. We don't know what it is at the outlet yet, but our temperature is pretty high compared to the critical temperature. Our pressure is really low compared to the critical pressure. So basically, since this has a high T, low pressure compared to T critical and P critical, we're going to assume that this is an ideal gas. The other thing is, it doesn't say anything about a large elevation change in our system. This is a nozzle. It probably doesn't have a large elevation change. So we're going to assume that the change in potential energy is 0. So anytime that you don't have a large elevation change in your system, and by large elevation I mean several meters, and probably more than that actually, you can assume that the potential energy, or the change in potential energy, is 0. We could also make an assumption that we can use constant specific heat because we have a ideal gas, so assume constant specific heat. And I think that's all of the assumptions for now. So now step 3 is to write down the equations we're going to use. So 3 equation or equations. Okay, so we have fluid flowing through a nozzle. The pressure and temperature are changing. The velocity is changing. So there's going to be some energy transfers. So basically, we need to do an energy balance to solve this problem, which is the first law. So we're going to apply the first law to this problem. And I'm just going to write out the entire thing. I had derived the general equation that you'll often use for nozzles in a previous video, but I often like to just start with the general equation and then cancel out what I know is 0 or what I don't need, rather than going to a nozzle specific equation, because first of all, the nozzle specific equation assumes that it assumes that your nozzle is adiabatic, so there's no heat transfer in or out. And in this case, that's true. But the problem is, what if you have a system where there is heat transfer in or out? So I just like to write down all of the terms and then cancel out what I'm not going to use. So this is the general energy balance for a steady stream, steady flow system. So we have a single stream steady flow system. There's only one stream in and out. We know that it's steady flow. That was one of our assumptions. So this is the general form of the equation that we can start with. So we have the change in kinetic energy plus the change in potential energy. So what I'm going to do before I move on to maybe some other equations we're going to need is I'm going to cancel out some terms that we know are 0. So first of all, we know this is 0. So the change in potential energy is 0. We put that in our assumptions, but it's because there's not a large elevation change over the nozzle. We know it's adiabatic. It's passive. There's no work. So we're left with this equation. So we have 0 is equal to m dot, and this m dot just kind of goes away too. So we have h2 minus h1 plus v2 squared minus v1 squared over 2. All right, so there are a couple of ways we can approach this. Basically, we know what these are, like the inlet and outlet velocities were given, and we can get this a couple of different ways. Basically, we're looking for delta H. We can look up H2 and H1 on the air table, because we do have a table with thermodynamic properties available for air. So I'm going to just list the two ways that we can solve this. So we're looking for delta H, and from delta H, from the enthalpy, we can get the temperature from the air table. So we can get T2. So let me write down the steps that we would use for that. So first of all, we would solve this equation for H2. So I guess in this case, it's not actually delta H that we need, but so we would solve equation for the enthalpy at the outlet, and we're going to get, so H1 is the only parameter that we're missing, so we would get H1, get from air table at T1. Once we have H2, so we solve this equation for H2, then we get T2 from the air table. So these are the steps we can take to get the temperature at the outlet from this equation. The other thing we can do, since we can assume constant specific heats, is, so I'm going to say this is B. Actually, I'm going to call this option 1 to solve for T1 to T2, and the second one is option 2 to solve for T2. So the other thing that we can do, and we only need to do one of these, I'm just showing you the two ways that you can approach solving this. The second way you can do this is you can assume constant specific heat, which we already did because it's ideal gas. So assume constant specific heat. And then the only issue with that is we really want to assume the constant specific heat at average temperature. So the issue with this is we don't actually know the temperature at T2 because that's what we're looking for. So what we can do is we can, instead of assuming the average temperature, we can, so don't have T2, assume temp at T1. So basically what we do is we get our specific heat at T1, and then we use that in our equation instead of the specific heat at average temperature. So if we use specific heats, we're going to have an equation that looks like this. So 0 is equal to C sub P average T2 minus T1 plus V2 squared minus V1 squared over 2. And then we would just solve this directly for T2. And instead of putting average here, I'm going to say this is C sub P at T1, which I'm just going to put the temperature. So that's at 500 Kelvin. Okay, so these are the two ways that we can solve this energy balance for the temperature at the outlet. The next part of the problem is to find P2. So second part, so we're still working on equations right now, like we're figuring out all of the equations we're going to use, and then we'll just go back and solve the equations. So for P2, first of all, we know that the mass in is equal to the mass out because it's steady flow. And we know that m dot is equal to the area, and I'm just going to keep this generic for now, the area multiplied by the velocity over the specific volume. And this is the specific volume, and this is the velocity. So what we can do is we can just say, well, first of all, we can, since we assumed ideal gas, we can get the specific volume from the ideal gas law. So we just know that PV is equal to RT. And so then the specific volume is equal to RT over P. And then what we can do is just replace this in this equation. So if we go over here, we have, let's just call this M2. This is equal to A2. Well, actually, let's just write, like, so we know that we have M1, and I'm changing the in and out to 1 and 2. So M1 is equal to M2. So we can just do this. We can say that A1, the velocity in, over V1, and we're replacing, well, let's leave it like this for now. And this is equal to A2 V2 over the specific volume at the outlet. Now let's replace the specific volumes with the ideal gas relation. If we do that, we get the A1. So basically I'm taking this and replacing both of these with the RT over P. So we have A1 V1 P1 over RT1 is equal to A2 V2 P2 over RT2. The R's are going to cancel because we have them on both sides. And we know that, and so now what we want to do is just solve this equation for P2 because that's actually what we're interested in. So P2 is equal to A1 over A2, V1 over V2, P1, actually I'm going to change this, so T2, and so I'm solving for P2 and just kind of rearranging the equation so I have like terms together. So T1 over T2, T2 over T1, and then multiplied by P1. And then we know that this A1 over A2, this is a 2-to-1 ratio, so we know what that is. So we know the velocities, we know the temperatures because we're going to solve for the temperature first, like in the first part of the problem, and we know the pressure in. So we have everything we need to solve this equation once we calculate what the temperature is. So let's just save this for now. Now I'm going to go back up. So we have all of our equations. So I'm going to go back up and we're going to solve our equations. So the first thing I'm going to do is solve this equation, not assuming a specific heat. So I'm going to show you how you would solve this using option 1. So we'd use the air tables to get H1 and then T2. And then I'm going to show you how to solve it using specific heats. So that would be with option 2. And once again, you can solve it either way since we have data available for air. So you would just pick one way to solve it. And then after we get T2, we're going to solve for P2 because that's the only quantity that we're missing in this equation that we need for P2. So let's go down here and start working on, so we're going to, since we have all of our equations now, and actually let me just go back up here and see what I called this. So look up data, solve your equations. So let's kind of do this together. So I'm going to go down here. So this is, actually I'm just going to call this data. So let's rewrite our equation. So we have 0 is equal to H2 minus H1 plus V2 squared minus V1 squared over 2. And what we're going to do, we want to look up H1 on the air table at T1. So T1 is equal to 500 Kelvin. And so if we look at the air table, which is table A-17, H1 is equal to 503.2 kilojoules per kilogram. So now what I'm going to do is just solve this equation for H2, and then I'm going to plug in the values. So we have our data from the table, so now we're going to calculate, or let's call this calculations. So calculations, and so I want to solve this equation for H2 because that's what I'm So I'm not actually looking for H2, I'm looking for the temperature at the outlet, but once we know what the enthalpy at the outlet is, we can just look up the temperature on the air table. So H2 is equal to H1 minus V2 squared minus V1 squared over 2. And this is equal to 503.2 kilojoules per kilogram minus, and then we have 380 meters, and remember to square this, so meters squared second squared minus 120 squared meters squared second squared, and this is over 2. And then it looks like we have some screwy units. We have kilojoules per kilogram and meters squared second squared. So since we're solving for enthalpy, so we're going to want kilojoules per kilogram, we need to convert the meters squared second squared to kilojoules kilogram. So the conversion for that is 1 kilojoule per kilogram is equal to 1,000 meters squared second squared. So we're just going to put this conversion in. So we have 1 kilojoule per kilogram over 1,000 meters squared second squared. So now all of these units should cancel out, and we should be left with kilojoules per kilogram, which is what we want. So then the enthalpy at the outlet is equal to 438 kilojoules per kilogram. And then we can go look at table A-17, and we get that T2 is approximately 437 Kelvin. And the way that I found that on the air table was I just looked at enthalpy until I found 438. So I looked at the column with enthalpy until I found 438, and then I just read the temperature off for that enthalpy. Okay, so this is the first option for solving this equation for the temperature. Now let's look at how we would do this if we wanted to assume specific heats. So I'm going to go back to I'm going to go back to this equation and resolve it using specific heats. So remember, you don't need to do this both ways. I'm just showing you both ways so that you know that you can do it either way. So 0 is equal to H2 minus H1 plus V2 squared minus V1 squared over 2. And then we're going to replace delta H with C sub P. And remember, this is going to be at, this was at 500 Kelvin, so this is at the entrance temperature, T2 minus T1. And the reason why I'm just using the entrance temperature is because we don't know what the outlet temperature is, so we can't very easily calculate an average temperature for the specific heat. So I'm just using the temperature at the inlet. So then let's rewrite this. So we have 0 is equal to C sub P at 500 Kelvin multiplied by T2 minus T1 plus V2 squared minus V1 squared over 2. And then we're solving for T2. So I want to solve this equation for T2. And I also need to look up the specific heat for air at 500 K. The specific heat for air at 500 Kelvin is equal to 1.029 kilojoules per kilogram. And I just looked this up on table A-2. So this is just something you'll look up, and this is for air. So let's go ahead and solve this equation for T2. So T2 is going to equal T1, and this is just some algebra, I'm just moving things around. So T1 minus V2 squared minus V1 squared over 2 multiplied by the specific heat, at 500 Kelvin. All right, so now let's plug in some numbers. So we have T2. So we should have everything. We know T1, we know the velocities, and we looked up the specific heat. So T2 is equal to 500 Kelvin minus, and then this is going to be 380 squared, don't forget the squared, meters squared, seconds squared, minus 120 squared, meters squared, seconds squared, divided by 2, multiplied by 1.029, so the specific heat, kilojoules, kilogram, Kelvin. So now we have kind of these screwy units again. We have, so we have the Kelvin here. That's going to go to the top. So that's the unit that we want. Everything else needs to cancel out. But we have these kind of screwy units again where we have meters squared, seconds squared, and kilojoule per kilogram. So we need to use our conversion. So 1,000 meters squared, seconds squared over 1 kilojoule per kilogram. So now the kilojoule per kilogram cancels, and all of these meters squared, seconds squared cancel, and we're just left with Kelvin, which is what we want because we're looking for a temperature. So T2, if you just plug everything into your calculator, T2 works out to 437 Kelvin. So that's basically what we got before. And I guess the only problem with doing this with the specific heat is if you had so if your temperature change was a lot larger than this, like let's say the temperature dropped several hundred degrees, that might make the specific heat assumption less accurate, since I was just assuming the specific heat for the inlet temperature. The outlet temperature was pretty similar to the inlet temperature, so assuming that constant specific heat for the inlet temperature didn't change the answer much. But if the temperature had changed a lot, then that might not have been as accurate. So in this case, it might actually be better to use the air table to solve your problem. But if you're working with a gas that you don't have tables available, then you would just have to assume a specific heat and make some sort of assumption about the temperature that you're going to use use to look up your specific heat. So that's why I wanted to show you both ways, even though you can just look the data up on tables for this problem. I wanted to show you both ways because there are going to be problems. Well, there's going to be gases, so like we don't have data for neon, argon, krypton, helium. So a lot of these other gases, you're going to have to assume a specific heat because you can't just look up the data on a table. So now let's do the second part of our calculation, which was to calculate the pressure. So I'm going to go back to this equation, and I'm just going to rewrite it. So P2, so now we're looking for the pressure. So P2 is equal to, and this was let's see, what was that? A1 over A2. So A1 over A2 multiplied by V1 over V2, and these are velocities, multiplied by T2 over T1 multiplied by P1. So we know that this is just 2 because it's 2 to 1. We know the velocities and we know the temperatures now because we just calculated T2. So P2 is equal to 2 multiplied by 120 meters per second over 380 meters per second multiplied by 437 Kelvin over 500 Kelvin multiplied by 600 kilopascals. So now these units cancel and we're left with kilopascals, which is what we want because we're looking for pressure. So this is equal to 331 kilopascals. So let's just summarize what we did. So we had this nozzle problem, and I just went through these steps. First I wrote down the problem information, did a drawing, made assumptions, and then I wrote down the equations, looked up data, and solved the equations. So you might not, these last 3 steps might, in some cases, blend together slightly, because you might be solving your equation and then you realize, oh, I need another equation for, say, ideal gas or some other quantity. So if you think that you have all of your equations written down or you can't think of any more, just move forward with solving it, and sometimes as you're solving it, it'll just become clear what other equations you need. But try and get as many of the equations you're going to need written down first. And so we have our problem set up, assumptions, equations. So we needed to apply an energy balance to this. It was single stream steady flow. It was for a nozzle. And then we had 2 different ways that we could solve for our enthalpies to get the temperature. And so we looked at how to solve it both ways. One was by looking up data on the air table. The other one was assuming constant specific heat at the inlet temperature. And then we found P2 by using this assumption that our mass flow rate in is equal to the mass flow rate out. We know that the mass flow rate is equal to the area multiplied by the velocity divided by the specific volume. And we were able to calculate the specific volume from the ideal gas law because we assumed that this was an ideal gas. So then we could write this relation where the only unknown was P2. So then we could solve for P2.